Hello, welcome to Curated. Let's start with the problem description of the question we will be solving today. Imagine you have been given a list of pair of nodes, something like this, where the first element in the pair is a parent node and the second element in the pair is a child node. And also, it's been given that a node can have multiple parents. You have also been given two nodes, say 6 and 8 in this example, and you need to find if at least one common ancestor exists between 6 and 8. If it exists, you need to return true, else you need to return false. Okay, by looking at this question, many try to solve this like a tree problem, which is wrong. It's not a tree, right? The question itself says that a node can have multiple parent nodes, so it cannot be a tree. It's a graph question. So, this type of graph problem is commonly seen in interviews at companies like LinkedIn or Meta. Okay, let me try to visually put these pairs as a diagram so that it will be easy for us to analyze the problem. Okay, let me start with the first pair. So, we have 1 as the parent and 3 as the child, and then we have 2 as the parent and 3 as the child. We have 3 as the parent and 6 as the child. And then we have 5 as the parent and 6 as the child. We have 5 as the parent and 7 as the child. We have 4 as the parent, 5 as a child. And we have 4 as the parent and 8 as the child. So this is a directed acyclic graph. From the diagram we can tell that this is a directed acyclic graph, and it's also been given that there are no cycles in the graph. Okay, so node 6 and node 8. We have node 6 here and we have node 8 here. By looking at the diagram, can we tell that node 6 and node 8 have common ancestor? Yes, we can easily tell that by looking at the diagram, they have a common ancestor 4. Correct? Yes, we return true in this case. So let's take another example, 6 and 7. Okay, 6 is here, 7 is here. Yes, they do have a common ancestor, so we return true. Let's take 3 and 8. By looking at the diagram, do you think 3 and 8 have a common ancestor? They don't have, right? So we return false in that case. Okay. Now try to think naively and see how can we solve this problem. Okay. I'll give you 10 seconds. Okay. So one naive way to solve this problem is from every node, try to traverse the whole graph and see if you encounter both 6 and 8. If you encounter, then yes, we return true because common ancestor exists because we started traversing from one single node. Okay, so we start from 4, yes it exists, we return true. If we started from 2, in case it does not exist, then we try with 1, then we try with 4, yes we return. So in the worst case, we end up trying all the nodes and try to check if a common ancestor exists, right, in the worst case. So what will be the time complexity in that case? It will be big O of n into big O of the time complexity of traversing the whole graph. It's n plus e, where n is the number of nodes and e is the number of edges. So it will be big O of n square, n into n plus e, big O of n square plus ne, right? But it's a very bad time complexity, right? So try to think of another approach to solve this problem. One good approach to solve this problem is, why can't we traverse upwards, right? From 8, you can traverse upwards and find that there is one parent node, right? And from 6, we can try to traverse upwards and try to find all the ancestors. Like for 6, we have 3, 1, 2, 5 and 4 as ancestors. So these are all the ancestors of 6. And for 8, we have one ancestor, that is 4. When we try to traverse from upwards and find all the ancestors for both the nodes, and if there is an intersection between those two ancestors, then we can say that a common ancestor exists. Let me explain. Take 8. Okay. What are the ancestors of 8? Just 4, right? Now take 6. What are the ancestors of 6? 3, 1, 2, 5 and 4. So we got all the ancestors of 8 and all the ancestors of 6, correct? And if you find the intersection between these two sets, what is the intersection? That is nothing but 4, right? So we have at least one common ancestors between 6 and 8. So we return true in this case. If you take 5 and 3 for example, 5 and 3. What are the ancestors of 5? It's just 4, right? Ancestors of 3, 2 and 1. So the intersection is, it's just an empty set. So there are no common ancestors between 3 and 5. So in this case we return false. Okay. And what is the time complexity in this case? It is big O of n plus e. Correct? Because in worst case we cover the whole graph and it's big O of n plus e. And we do it for 2 nodes. So it will be 2 into big O of n plus e, which is nothing but big O of n plus e. So this is acceptable time complexity for this question. So during the upward traversal, what we are basically doing is, from 6 we are going to the 6's parents, that is 3 and 5. And from 3 we are going to 3's parents, that is 1 and 2. And from 5 we are going to 5's parents, that is 4. So basically we are accessing its parents and going to them, and from there we are going to their parents. For that we need a data structure from which we can easily get the parents of every node so that we can move upwards, correct? What data structure can we use in this case which will easily give us the parents of the node that we want? Think about it. So we can use a map, right? Where key will be the child node and the value will be the list of its parents. For example, if 6 is the key, the value will be its parents, that is 3 and 5. If 3 is the key, then the value will be 1 and 2, that is the list of its parents. So like that we can build a map of child and parents list for every node. So now let's start building the child parent nodes map. Okay, so let's start from the first pair. So we have 1 comma 3 where 1 is the parent of 3. So 3 is the child and 1 is the parent. Next we have 2 comma 3. 2 is the parent of 3. Next 3 is the parent of 6. 6 is the child, 3 is the parent. Later we have 5 comma 6. So 6 is the child, 5 is the parent. Later we have 5 comma 7. 7 is the child, 5 is the parent. Next we have 4 comma child. 5 is the child, 4 is the parent. Next we have 4 comma 8. 8 is the child, 4 is the parent. So now we have built the child and parent nodes map. So now we can easily access the parents of any node using this child parents map. So on average it's big O of 1 time complexity to get the list of parents of any node because it's a map. Now the upward traversal, I will be doing it using depth first search approach. I will be doing iterative DFS traversal using stack. So let's proceed with that and see how we can solve this using stack. So I will be creating a stack data structure. We need to find all the ancestors of node 6. Okay. In the beginning, I start by putting node 6 onto the stack. Okay. Then I'll start iterating over the stack. So first I pop the top of the stack. So the first element that I'll be popping is 6. So 6 has parents as 3 and 5. Okay. So actually before this, let me create a data structure ancestors which will be a set. Okay. It will be a set and it will hold all the ancestors of 6. So at the beginning it will be empty. Why set? because we'll also use it to check if we have visited a node more than once. We get 3 and 5 at the beginning. So first let's take 3. Have you visited 3? Is it present in the set? No, right? So we add it to the set and we also add it to the stack. We should also remove the 6 from the stack. The next element is 5. Is 5 present in the set? No, it's not. So we add it to the set and then we also add it to the stack. Now the iteration for 6 is done. Now we will pop out the top of the stack. So this time we will be getting 5. So what are the parents of 5? 4. Is 4 present in the set? No, it's not. So we add 4 to the set and then we also add 4 to the stack. We have popped out 5. So I'll be removing that. The next element that we get from the stack will be 4. We see that 4 is not present in the map, right? So we will skip this iteration. We will go to the next iteration and we pop 3 from the stack. So we get the parents of 3, that is 1 and 2. Is 1 in the set? No, right? We add 1 to the ancestor set and we also add it to the stack. Later we go to 2 and is 2 in the ancestor set? No. We add 2 to the set and we also add 2 to the stack. So now we pop the top of the stack. So it will be 2 now. Is 2 in the map? No. So we skip this iteration. So now we pop 1 from the stack. Is 1 in the map? No. So we skip the iteration. And now we see that the stack is empty. So we will stop our iteration and we have got all the ancestors for the node 6. Okay. Let's try to do the same for 8. Let's try finding all the ancestors of 8. So first let's add 8 to the stack and in the first iteration we will be popping out 8 from the stack. We'll also maintain a set for its ancestors. Is 8 in the map? Yes. And what are the parents of 8? 4. Is 4 in the set? No. Add it to the set and add it to the stack. Now pop out 4 from the stack. Is 4 in the map? No. So skip this iteration. Now we see that the stack is empty. So we are done with finding all the ancestors of 8. So we have all the ancestors of 8 and all the ancestors of 6. Now iterate over one of the ancestor set and try to see if that ancestor is present in another set. So when you do that, if it is present, then a common ancestor exists between the two nodes 6 and 8 and you return true in that case. In this case, we see that it exists, right? 4 is common in both, so we return true. As discussed, the time complexity would be O of n plus e, where n is the number of nodes and e is the number of edges, because we will be traversing over the entire graph. And the space complexity would be O of n for storing ancestor sets and the stack. So this was the dry run of the solution. So let's start coding the solution now. So let's start coding the solution. We have shares common ancestor method, which takes the parent-child pairs node 1 and node 2 as the input. So let's begin by creating a child parents map, which will be a map of integer and list of integers. So let's call it child parents map, which will be a hash map. So let's iterate over the parent-child pairs. So the first element would be the parent. The second element would be the child. Let's update the child parents map using compute if absent. So if the child exists in the map, it returns the list of parents, else it returns an empty list. And to it we add the parent. So we have created the child parents map. Now let's try to get all the ancestors of node 1 and node 2. So I'll be creating a separate method for that functionality to keep the code clean. So I'll be returning a set of ancestors. Let me call the method getAncestors, which will take the child parents map and the node for which we need to find the ancestors as the input. So we will be solving this using upward DFS traversal, iterative DFS traversal. So we'll be using a stack for it. So let me create a stack. And let me add the node as the first element to the stack. Let me also declare the ancestors variable, which will be a hash set. It will also help us in avoiding the visited nodes. Okay, so let us traverse over the stack as long as the stack is not empty. As long as the stack is not empty, let us traverse over it. So let us pop the first element from the stack, which will be the top of the stack. So let's call it current node. So let us check if the child parents map has this node. If it contains the key, current node. If it contains, then get all its parents dot get current node. So get all its parents and iterate over the list of parents. So check if the parent has already been visited using the ancestors set. So check if it is already visited using the ancestors set. If it is visited, we don't have to add it to the stack again. So if it is not visited, then add it to the ancestors set and add it to the stack as well. So we have traversed from the node to its parents, then to the parents of its parents, then to its parents. So by doing this, we have collected all the ancestors of the node. So now let's return the ancestors. So now let's call this functionality for node 1 and node 2. So let's call it for node 1 first. It will be list of, sorry, it's not a list, it's a set. So we get ancestors for node 1. Similarly, let's get the ancestors for node 2. So now let's try to find if any common nodes exist between ancestors 1 and ancestors 2. So let's iterate over ancestors 1 and try to check if ancestors 2 contains this ancestor. It will be a big O of 1 operation on average because it's a set. If it contains, then a common ancestor exists, so we return true, else we return false. So let's try to run the solution. I ran the output on a couple of inputs. and we got the expected output. Hope you understood my explanation. Thank you.